This section is a little bit different. I'm not even going to give you an assignment out of this section directly. Some of the stuff we do in it, we've already done problems for, and then some of the stuff in this section we'll kind of hit a little bit later. This section is really just talking about how this process of finding the derivative relates to a bunch of different fields. So some people have the philosophy that if you're just doing math for math's sake, what we would call doing theoretical math, then it's not doing anybody any good because you're not like using it for something. You're not like solving the problems of the world or anything like that. But sometimes when you're doing math for math's sake, when you're doing theoretical math, you will come across something like the derivative, and then it turns out that it has a bunch of applications that we find out later. So calculus was developed for a purpose, but it turns out it not only serves that purpose, it serves the purpose for lots of other things too. So we're just going to kind of look through some of these problems. Hey, don't sweat it if some part of it, you don't perfectly understand or anything, because again, we're not going to have to like work these exact problems or anything. A lot of it, if we're talking about like the different sciences and things like that, if you're not well versed in that particular science, then a lot of it might just be a bunch of jargon. That's okay. We're just kind of looking at how this calculus stuff we're doing applies in several different fields. So take that for what you will. So here's what we've been doing. I've been talking about the derivative, dy dx. We'll see that notation in here a pretty good bit. And if we're thinking about, we'll go back to kind of thinking about it in terms of rate of change. Okay? We call slope rise over run. Right? We're thinking about how our dependent variable changes with respect to our independent variable. So we had that delta notation that gets used for that. And then we're thinking about it that way. Another interpretation of that, right, we've seen is like the slope of the secant line to a curve. And then when we go through our limiting process that we've developed, we can get the slope of the tangent line, which is instantaneous rate of change, is one way of thinking about that. That's just our difference quotient again. So we haven't used it much, but remember we can think about our derivative as like this instantaneous rate of change that we have here. That's with the delta notation, which is how you'll see it in a lot of fields. Okay, they'll use the delta notation because it's maybe a little bit easier to interpret in some situations. Okay. We're just going to kind of go through several different areas of study and look at how this gets used. Okay. So first we got physics, which is natural. That's really how calculus came about. Okay, was to solve physics problems. So this is the one we're most familiar with already. The big takeaway here that we've had is that if we have like the position formula for something, so there's an equation for the position of a particle, then if we take the derivative of position, we get velocity. If we take the derivative of velocity, we get acceleration. And we actually mentioned we can keep going. Get down to the funny ones like snap, crackle, pop. So the nice thing about this, we've got a nice little polynomial, and we can do derivatives without too much trouble. We can get velocity, we can get acceleration. The more interesting part of this example is looking at like C and D. Okay? It says like when's the particle at rest, and then when's our particle moving forward, when's it moving backward? We can think about things like that. So we'll skip through some of this, right? We might as well get a little derivative review in though. We've got our position function, and we want to find the SDT, which would be velocity. We use the power rule. Doing that, okay, we can do the same thing again for acceleration. Well, let's kind of want to get to the graphs. So we take our position S, the pink one, and we find the velocity and the acceleration. Okay. We can get a lot of information from just having those three graphs together. Okay. So like if our acceleration is positive and our velocity is positive, that would be our particles moving forward. Right? So starting here, we know our particles moving forward, and it's speeding up. Okay. Before that, okay, where our velocity is negative and our acceleration is positive, right, then we're actually slowing down. Things like that, or can be, with a little bit of practice, can be easy to pick off the graphs of those things. So it can be really useful. Okay. Beyond just plugging in numbers and trying to get a direct numerical answer to something, graphs can be really helpful there. And we'll, next test, okay, we'll deal with a lot more stuff about graphs of derivatives. So that's that one. Let's see. That example we'll skip through because it's boring, okay, to me. Another application, okay. Even if you know some about electricity, if you haven't thought about it from a physics standpoint, then you kind of have to stop and think about this one for a second. So we have a charge that's moving. Okay. That's typically what we call current flow. And really what we're thinking about is we're thinking about charges moving past like a fixed point on one axis. So we end up with, in 3 dimensions, we end up with charge moving through a surface. Charge moving through a surface. We can find the average current. Okay. Just find the current at one place, the current in another place, subtract them, and then over the time difference. Okay. But if we take the derivative, okay, we get the instantaneous current. So anything right there? Maybe some of the physics people, some of the engineering people have got coulombs per second there for our current there. Amps, right? Yep. So look at some chemistry. You might not think about using calculus in chemistry as much. Okay. Because we don't think about movement quite as much in chemistry. Okay. So how many of you have had to take a chemistry class? Right. Most of you. Okay. So you've seen you had to balance little equations like this one. So we've got two chemicals we're putting together to make another chemical. And then you've had to have chemistry, you've had to deal with concentration. Okay, so you got the molar units of things there. So here we're thinking about like how fast a chemical reaction happens. Okay. So we could get the average rate, right? That's not a constant thing, right? So it's not necessarily linear. Right? Maybe it starts off fast and then it slows down and gets toward the end, or the other way sometimes. You know? So when we take the limit, okay, we get the instantaneous rate of change. Right? So we can figure out the instantaneous rate that our reaction is happening at. So maybe we want to know how fast a chemical reaction is going to be happening after 5 seconds, or something like that. And we get calculus involved. Okay. you don't necessarily do that in like the first couple of general chemistries or anything, but because the calculus is not a requirement in there, but something to think about. Okay. Dun, 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 dun. Here's another one. This one gets lumped into chemistry. Come on. This one gets lumped into chemistry, but you could think about it as physics too. A lot of chemistry is that way. So if we've got a fluid, and we have this pressure, temperature, volume relationship, and here we're thinking about holding the temperature constant. So then as you decrease the volume, the pressure increases, and you squeeze it, and the pressure increases. And that change is not necessarily the same for every fluid. So when we think about that, we call it compressibility. Okay? And that involves the derivative. Okay, we're thinking about the rate of change of the volume as compared to our pressure changing there. Okay? That comes in another place. Okay. We won't get too deep into that one. There's a couple more that are a little more interesting, so we'll spend a little more time on those. Am I not thinking about using calculus in biology? Okay. When we're thinking about how a population of organisms grows, okay, or decreases, grows or dies out, then we get a rate of growth there. And if we want to know how the population is changing in size at a specific time instant, we need the derivative. We need to take the limit and get the derivative to get our instantaneous rate of growth. Okay. You can talk about averages, but sometimes we want to know the instantaneous value. And it kind of gets ignored if you're not already initiated into calculus. It seems like a easy question, just thinking about it. Like, okay, what's my growth rate after 4 seconds of some bacteria or something? But really, if we want the instantaneous growth, that's a calculus question. Okay. Kind of hard to imagine people not being able to answer questions like that before calculus. You could estimate it, but you couldn't get there exactly. Okay. One thing to point out here on this one, and this comes up a lot, okay, in practice, but if we're just taking the measurements, like of how many individuals we have in some population at different times, that would really be a step function, because we can't constantly measure like how many of something we have. Okay. So we would actually have a step function like that greatest integer function. So it would not be continuous everywhere. It would have all those discontinuities. It would be non-differentiable at all those discontinuities. But what we do in practice is we have a curve that we use to estimate. So you can get a curve to fit that data as closely as you want it to. And then we can use calculus. I got a nice smooth curve. We do have some approximations in there. Let's see. Bacteria growth. This one's a little interesting. Maybe something that I got a random alarm going off on my phone. Maybe something you don't think calculus would come into, but you need it when we're talking about blood flow. So here we're almost kind of in the biomedical engineering like type of area here, because we're talking about laminar flow through blood vessels. And so got some things there. So with laminar flow, what we're thinking about if we've got blood flowing through an artery or something, okay, it typically flows slower toward the wall of the artery than it does through the middle part of the artery. It has got more like friction with the wall, things like that. Okay. If you have too much of a discrepancy there, you get turbulence, and then that changes the flow characteristics up a whole lot. Or if we don't have much of a difference, you get laminar flow. So we've got equations for that, and we won't get into all the nitty-gritty details since we're a calculus class and not a biology class, but we can calculate that. Okay? We can calculate that. If you're trying to do something like design an artificial heart or something like that, right? You need to be able to calculate the flow through there. Comes into play. Okay? And then we get it coming into the business world a little bit. Place you might not imagine calculus being, but it's very prevalent. Very prevalent. So we've talked about this one just a tad. But if we've got some function that tells us how much it costs to build some product, then we can talk about the rate of change. So then we can talk about the instantaneous rate of change. So in economics terms, if we talk about the instantaneous rate of change, we're talking about the marginal cost. That changes, right? You've heard the term economy of scale. And so if you're building more of a particular product, you can do each one cheaper than if you're just building like one or two of them. That's not a constant. Again, this one's kind of like the biology when we looked at, since our value is only changing, our cost is only changing for each product, we really have a step function, right? So it kind of goes up in chunks instead of being a nice smooth curve. So we have to come up with an approximating curve for that. And then we can take our derivative. This one's actually a pretty nice problem. Okay, got our cost function, and then give you the marginal cost if we take the derivative at the 500th item. So that's saying when we get to 500 items produced, it's costing $15 per item. Our derivative evaluated there. It's in there if you want to look at it. It's all over the place. So here's just a few more places where calculus would come into play. Okay. We've got an example of molten rock cooling for geology. Water flow rate into some reservoir. You have to take differential equations. That's a really popular type of problem that you get into there. We got things thinking about like where people move around, thinking about population density, and then all kinds of weather stuff. Okay, we need calculus. So it's not just we kind of get lost on it. It's not just the Bob buys 725 watermelons, type of math problem that we come up with something goofy because we're trying to just learn the math part of it. Okay. So the downside of doing that, okay, is that we kind of lose touch with what we're doing sometimes. But the reason why we do that is when you're working on real world problems, the numbers are usually not all that nice. And you got crazy things that you have to consider, like with the physics, even in physics class, they're like, ignore air resistance. And you're like, air doesn't exist, but it does, right? So you just kind of try to do the simple version when you're first learning this stuff, and then you can add in all the extras that you need. Just like here, all these different fields, there's some little tidbit that you have to tweak as you go from one place to the other, but the root of it all, is the same. Thoughts or questions? Anything? So that's the selling point, part of the selling point on while you're in here. Okay. If you just, depending on who you hang out with, I guess, you don't just hear people talking about calculus stuff all the time, right? But it's everywhere. Okay, it's everywhere. Surrounded by it, you're just kind of behind the scenes. Kind of behind the scenes. All right. Yep. No, because not necessarily because on these, you got all this background information you need, like what was that left one there? Yeah, like when we got laminar flow, right? Then we've got this term that comes in, and if you're studying physics and you're studying about fluid flow, then this is going to be something you're dealing with all the time, so it's something you know. But we got this like new Greek letter nu term in here for the viscosity, and we can't count on everybody to know about viscosity. I don't know that much about it, right? So we can't have as cool of example problems. Yeah, we're going to be more along watermelon style stuff. Now, so Monday we'll start dealing with not necessarily these types of problems exactly, but doing some word type problems with derivatives called related rate problems. Okay? And typically ours are going to be like geometry related, where we can say, here's the formula for volume of a sphere, take the derivative. Okay? Or here's the area of a rectangle, which you probably all know, right? Length times width, take the derivative. And so it'll be more generic math related stuff. But you can do the same thing in all these fields. It's just that sometimes we have a bunch of background knowledge that we need. This there. I think anything else? But also, let me give you the other side of it. Because I remember when I started learning this stuff, I was like, wow. So if you take enough math, you can basically solve like any problem, right? That's what it feels like. So there are lots of stuff, okay, that math can deal with, okay? And if you get deep enough into it, you start realizing how much stuff it can't deal with. Okay? So there are lots of problems in the world that you encounter that it doesn't matter how good you are at math up to this point. Okay, we've got lots of stuff we can't solve. So it's not either extreme. It's not either extreme. It's not useless, and it doesn't solve everything. Okay, somewhere in the middle. Let me give you one that's like one type of problem. It's just interesting side note, not calculus related. Let me give you one that's really simple problem. Everybody can understand it, and we can't get an optimal solution. You can estimate it, but you can't get for big cases, for larger cases. So you may have heard the traveling salesman problem. I know that. Sorry, say again. The shield zone. No. No, that's yeah, I know that one. This is like real world problem here. Traveling salesman or saleswoman. Okay, traveling salesperson. No, not necessarily. The Hilbert Hotel. Yeah. So, okay, simple problem. Okay. Let's do like a really easy version, and we'll localize it. And here we go. Okay, so we've got a salesman. He needs to make a trip and go to all three of these cities. He needs to know what order he should do his trip in so that he's traveling the shortest distance. Okay. This one's super easy because we only have three cities. Okay. So on this one, so let's just I'm gonna make up numbers. Okay. I have no idea how. That's probably pretty far, so we'll call it 400. So just totally made up numbers here. Okay. But if we wanted to solve this problem, how can we do that? Well, we could like start at Atlanta and say, okay, if we go to Miami and then Birmingham and then back to Atlanta, okay, so maybe it lives in Atlanta. Right? So that's where it's got to go back to. How far would that be? Or if it goes to Atlanta and then Birmingham and then Miami and back to Atlanta, how far would that be? This one's the same both ways around because we've only got 3, so we do just make a loop. It gets harder if we throw in like another city. So throw in like Charlotte, North Carolina. Well, maybe not. Let's do Charleston, so because I know how to spell that. Okay. So now I won't even put numbers on it. But now, what are our possibilities? Like we're starting Atlanta, so it could go Charleston, Birmingham, Miami, or it could go Birmingham, Miami, Charleston, or Birmingham, Charleston, Miami. And now all of a sudden we've got more possibilities. And so we'll call that like our N number. Our N number. We could brute force that one, no big deal. High school student figured that out. When you start getting into trouble, it's when our numbers of cities get a little bit bigger, and they really don't have to get that much bigger. Even when we get to like 10 cities, the number of calculations you have to do to find the optimum route grows really, really quickly. It grows in a factorial manner. Factorial, where like, so 3 factorial means 3 times 2 times 1. You do the number you start with times the next number down times the next number down. So we talked about exponential growth being really big. Factorial growth is even bigger than exponential growth, even faster. So like by the time, I forget exactly where the number is, but like by the time you get to like, I don't know, you got a UPS man that's got to make like 20 stops today. Got to drop off 20 packages. What's his most efficient route? Somewhere in there, maybe it's like 25. That problem has so many calculations, you could take the best supercomputers we've got, run them for 1,000 years, and you wouldn't be done. And then, if we've got n's bigger than that, you start getting up into bigger numbers. Then you can take the best technology we have and run them for as long as the universe has been in existence, and we don't have time to do all those calculations. The advanced medical technology. Yeah. Like eventually, would the computer get there? Or eventually, we'll be able to do it. Maybe because they're doing stuff like with quantum computers and things like that can get a little better. So here's the issue: if you work for a company like UPS, this is a huge problem that you want to know the answer to. And it's not just traveling. Okay, this same type of problem where it just grows so big you can't handle it anymore, even though the numbers are like reasonable stuff that you would want to do, like make 40 stops on a trip. Those are really big money problems. Okay, so it's not that we get the optimal solution. I'll be right with you. It's not that we get the optimal solution. UPS is not going out of business, right? But what they have is we've developed methods where we can get good solutions. It may not be the best solution. That's pretty much unsolvable. But you can get good solutions, good enough. Yep.
Basically, the difference between P and NP problem?
Yes. Yeah, that does boil down. Yeah, so when he's talking about there are problems that we can solve in what we call polynomial time. So like when you're calculating how many calculations you'll have to do for a certain problem size, it comes out to a polynomial formula. Those we can do with technology, no problem. Okay. But when we get into the NP problem set, those are what we call non-polynomial. So typically what we mean there is it's growing faster than the polynomial, and that's things like factorial. Get into issues there. But it's a simple problem, right? Like what order should I make my stops in? If the n gets very big at all, that's like unknowable. The best solution, the optimal solution. All right. So anyway, not calculus related, but math related, so we're okay on Friday. All right. All right. Have a good weekend. We didn't. Hang on a second, I'll catch you up.